Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently working as a university researcher over in the University of Helsinki in Helsinki, Finland. And I'm a cosmologist, so that means that I study the universe, the content of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a scientist, I love studying cosmology, and I love chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about space, about physics, about cosmology, about academia, about Finland, about my new job title, about my cats. You can literally ask me anything and I will do my best to try to answer your questions. This means that the direction of the stream is entirely up to you all. For anyone who's a first-time viewer, welcome. Great to have you here. For the people returning, I see we have some of the regulars already in the chat. Welcome back. It's great to have all of you here. If you haven't done so yet, please do subscribe, like the video, leave a comment. All of the usual YouTube or Twitch things, whichever platform you're watching on. Press buttons, make stuff happen. I really do appreciate it. I see we have some of the regulars here. Lethargo, Brath, Ben, Scott, Ange, Paul. Great to see you all. Welcome back. It's been a few weeks. It's been like 3 weeks since my last Cup of Cosmology stream. Mainly because I've just been busy. Now, I feel like I've been busy for the last 5 years, but especially the last few weeks, it's just been insanely busy. But all good, having fun, doing a lot both at work and in my social life. But it just means that sometimes Cup of Cosmology has to take a break. But we're back today. Not yet sure about next Sunday, but I'm back today. So this is your chance to ask anything you've been wondering about cosmology, about space. If you've seen anything in popular science news recently and you want to fact check it, I'm always happy to do that. There are sometimes some claims in popular science articles that are potentially a bit exaggerated, so I'm always happy to slightly debunk those. No, they're not wrong, they're just interestingly worded sometimes. And I am thinking about a specific thing that I've seen in the news this week. But if someone asks about it, I will answer. I'm not going to bring it up otherwise. But I see we had one question already before I started. You got your question in 10 minutes early there, Space Goes Supreme. Any news in 3L Atlas? So the fact that you got your question in 10 minutes before the stream started meant that I could quickly look it up. No news as far as I'm aware. So for anyone who hasn't heard, 3L Atlas is a comet that was discovered back in July this year, and it's going to have its closest approach to the sun in October, in about a month. So it should be, I think it should be visible at some point soonish. But I learned about this very recently, as in 10 minutes ago. But yes, it is a comet that should be visible at some point soon, but I don't have any further news other than it will be visible at some point in October. And comets are always fun to look at because they're often once in a lifetime things. Comets will sometimes come by and then go off and, travel freely or travel in its orbit and unlikely to come back within proximity to the Earth anytime soon. So often seeing comets is a once in a lifetime thing. Or not seeing a comet, but seeing a specific comet. So if there is a specific comet, it's comet, not comment. I was reading comments. Comet. Yes. If there's a specific comet in the night sky, it's always good to check it out if you can, because you might not see that comet again, but there are other comets around. Okay. Question from Angia. Tell us about your new job title and what new things you're working on. Thank you for the question. So some of you might, if you were in my last stream, you've heard the announcement. If you weren't in my last stream, you get to hear it now. And if you've heard it before, you hear it again. I recently got a job title promotion or a small job promotion. I am no longer a postdoctoral researcher. I am now a university researcher. That means that I'm slightly more senior than a postdoc, still not as senior as a junior professor or something like that. It is still a short-term contract. I also, together with a job title, I signed another 2-year contract. So I now have job security until the end of 2027, which in academia is quite a lot, actually. So it's still not a permanent contract, permanent job, but it does mean I'm now slightly more senior than a postdoc and I have more responsibilities and a slight pay rise to go with it as well, which is nice. The job title, the promotion was backdated to July, which is the time at which we initiated the discussion to do this pay rise or this job promotion. And thank you for the congratulations. A lot of you sent me messages after I announced it in the stream 2-3 weeks ago. It's become official in September. I've known that it was happening for a while now, but I've officially been allowed to share this news since September. And someone sent me a bunch of coffees on Ko-fi to celebrate, so thank you. That was very much appreciated. I very much appreciate all of the people who support me on Ko-fi. As always, Cup of Cosmology is and always will be free, but there is the voluntary option of giving a coffee, a donation of however much you please. The link is always in the YouTube description, but there is absolutely no pressure whatsoever for anyone to ever do so, and I'm deeply appreciative of the people who do click that button and send me a coffee. It really means a lot to me. As to what I'm working on now, so for the last year, I've been splitting my time between research and managing my cats. Do not drink my tea. That is mine. I said, managing my cat. A cat just walked across, just out of the camera, but just walked across the desk, which is why the keyboard is immediately turned off when the cat jumps on the table. I'm fast reacting to that now. So for the last year, I've been working on research while also managing our data center, the LISA component of our data center. So just going to give a quick overview because I talk a lot about data centers, but I don't really explain what they are. So space missions, both current and future space missions, require a lot of computational resources. We generate a huge amount of data. We have extremely advanced computer codes that need to analyze and process this data. And all of this is going to need a lot of both computing power and storage and person power to actually deal with all of this. So in order to manage this data, we use what are called data centers. And data centers are basically supercomputers or clusters or servers, big things where you can do a lot of computation. So this is much more advanced than a laptop. This is usually a collection of servers dedicated to these space missions. Now, in Finland, we have a data center called the Cosmology Data Center Finland, very imaginative title. The Cosmology Data Center Finland is handling resources for both Euclid, an ongoing mission that was launched July 2023. 2023, yes. And LISA, which is the Laser Interferometer Space Antenna, a gravitational wave detector that is set to launch 10 years from now. So the Cosmology Data Center Finland is managing data for both of these missions. We're obviously not the only one. There are a bunch of data centers across Europe. In the case of LISA, there are 12 data centers planned, mostly in Europe, one in Canada. And all of these contribute to handling the resources that we need for LISA and Euclid. Now, you might be wondering what we need to do with LISA by now, because LISA doesn't launch for another 10 years. So while for Euclid we do have ongoing data, for LISA we don't yet have real data. However, once we get the real data, we need to be ready to analyze it, to unpack it, to look for all the possible signals and all of the cool gravitational waves we hope to find there. You know, LISA might find everything from black holes smashing together, small black holes falling into big black holes, to things like the ripples left in the background of the universe by the birth of the universe, or the very first seconds of the universe. And all of these are things that we hope to find in LISA data. But we need to start preparing now. So we need to prepare all of the tools, all of the software, all of the data analysis techniques that we will need once we get the real LISA data. So in order to do that, we use what is known as mock data or fake data. So we create a data set that we try to make as realistic as possible. And this is what we call mock data. So it's data that will have a bunch of things that we expect LISA to see, plus the instrument noise, plus things that are going to get in the way, like our galaxy. And we put all of these signals in our data. We put some random scattering noise around it. And then we try to recover what we put in the data. So we try to find the signals. Now, in this case, we have the advantage that we know the truth because we put it there. It's fake data. We know what's in there. So we can test our analysis pipeline, see if we manage to get back what we put in. And if we do, we know we're ready for the real data. Now, LISA is set to take data for 4 years, taking a data point once every 5 seconds. So this means there's going to be millions of data points. And it's very difficult to process all of this data. So we're currently at the stage of producing this fake data on one of the data centers and then analyzing it. We've done this a few times already. Currently, actually, like right now, currently, as in this month and next month, we are producing the next big mock or fake data set for LISA. It is the most advanced data set we've been able to do up till now. It is 2 years of data that we're producing, and it's going to have a bunch of overlapping signals. And then everyone working on LISA, data science, can play about with this data and figure out what might be there. Now, this fake data that we are producing right now is being hosted and produced on the Finnish Cosmology Data Center, and this is what I've been kind of overseeing and managing for the last year. So I've been managing the LISA part of our data center. I have a counterpart managing the Euclid part of our data center. And it's basically been building up to what is happening right now, which is this data production. Of course, we're going to keep doing other things for the next 10 years. Ideally, with our data center, we have funding for at least 5 years for the data center. But it's pretty cool. So in answer to the question of what am I working on currently, I have my research ongoing, which is in gravitational waves and dark matter. But also I'm managing the LISA component of the Cosmology Data Center Finland, which means getting everything, making sure we have all of the resources and that we're ready to host the production of this fake data. And it's kind of exciting because this is something we've been building up to for months, and it is really kicking off right now, which also means now is the time when everything needs to be running perfectly. So it's kind of scary, but it's also super fun. And it's really nice to be involved in the Cosmology Data Center. I recently wrote a blog post basically summarizing everything I just said about the Cosmology Data Center. So the question was, what am I doing with my new job title and so on? So the reason I'm now a university researcher partly is because of the added responsibility I have while managing the data center. Starting from next week, I will be increasing my research time and slightly decreasing my data center time because I got a research grant to focus on a very specific research topic, which I'll tell you more about next stream once I'm actually working on the grant. But I'll still be managing the data center as well. And I think you just saw the cat walk back over that way. So yeah, university research is the new title, and I'm doing a lot of cool stuff, including managing a data center, which is very, very fun. And I see there's some comments related to this, and then I'll go back and answer some other questions. There was just one question from Paul here at the end. Can you sneak in the couple cosmology logo art encoded into the fake LISA data? I haven't done yet. I haven't considered sneaking in my own things into the data. I don't think people are trying to sneak in sneaky stuff. I know you could call it a noise where when you pull it out, we can't do that in the official LISA data, but there's no reason why I couldn't do that on the side myself and just like inject a random image and see if I can pull it out, like the 2D one. There's a comment from Ange, that's a lot of data, sounds like a lot of work. Indeed, this is why we're preparing for 10 years before the mission actually launches. Because, we're spending a lot of money to send this very cool detector to space. So it would be a shame if we don't then have the technology to analyze the data. But fortunately, we have 10 years to prepare for this. At least 10 years. LISA will launch in 10 years. The first data will be available in like 11 or 12 years. So we still have time. Okay, sticking with data center and stuff like this, and then I'll go back to the other physics questions. And I know there were some more comments about the comets that I was talking on. Okay, the comment I was talking about just now. There was the question from Paul here. One thing large language models have shined in is coding. Have you or your colleagues begun to use it much for that purpose? I would completely disagree about large language models being in any way good at coding. Now, large language models are essentially a glorified chat predictor. They can tell you what is a likely answer to this question. What would an answer to this question look like? But they're not actually answering questions. Now, if you ask a large language model to write a code from scratch, it is not going to be able to write a code that does exactly what you want it to do. You can get very simple functions. You can get it to do simple things. But if I told if I asked ChatGPT or Copilot or whichever one you want to pick, write some software that will analyze LISA data, it will not know what to do. Of course, then you can refine it, like, okay, make a software that will analyze a time series and you can get hints and prompts. Now, I think if you're going to use large language models for coding, it should be done in the way of kind of like, can you help me debug this code? Can you check that this code is succinct enough? Is it accurate? Is it producing the same results every time I run it? But getting it to write the code from scratch is something that I personally would not trust it to do. Now, I know some of my colleagues do use large language models to refine their code, but not to write it. And in fact, a lot of places have very strict guidelines on this, especially when we're developing software for something like Lisa. There are very strict rules on how much we're allowed to rely on large language models, because this is software that eventually is going to be in the public domain, and we need to confirm like who did it and what's it based on. There are some things like if your university has its own large language model trained on your own research, that's something that you're allowed to use, but it gets murky. So personally, I would not trust a large language model to write a code from scratch. However, I might trust the large language model to do something like check my code for, missing commas or something like that. But for that purpose, we also have very good IDEs. There are already programs that do this. If you code in VS Codium, for an example, or in any of the JetBrains software, this is already a built-in feature, built-in functionality. Now, I'm coming at this from the angle of someone who is very, very skeptical of large language models, especially because I think the use that we're getting out of them does not justify the energy resources that are being consumed. And I'd much rather power up my IDE, my usual coding software, which will help flag bugs. And I'd much rather do something like code review, where I share my code with a colleague who can then check over it and we collaboratively build this code, rather than asking a machine to basically burn a rainforest in order to help me with my code. So personally, I don't think large language models are being used extensively in coding in my direct group and area, but I know some people are using that. Now, as Lothargo was just saying here, for as a non-scientific programmer, LLMs can be useful for learning or lookup tool, absolutely. So it can be useful as a reference. There's much code that I've written that has been cross-checked with Stack Exchange or Stack Overflow. I always forget which is the actual name there. So checking code against existing books or existing literature, asking on a forum, this is something we've done for years. This is how coding has always been done. And if now you want to ask LLM instead of large language models, instead of, asking Google, sure, that is good. And I think for this type of thing of how would I write a function to do this, it's great, but not write a code to do this. So I think it's good for quick questions or for proofing a code, but not for writing a code from scratch. So I personally would not use it. I am highly skeptical of large language models myself. One of the things I love about being a coder, about writing software, is I know exactly what it does because it does what I tell it to do. And if it does something stupid, it's because I coded it badly. So by working on a code, by developing a code, by writing it myself, I have full understanding of what I'm doing. It's not a black box that I'm throwing numbers into and getting numbers out of. Of course, there is some software I use that I don't know exactly what it does, but I can open it up and trust myself to kind of follow along what it's doing. Whereas if I ask a LLM or a ChatGPT, write a code for me, how do I know that what it's doing is correct unless I go through and proof everything? And if I'm going to do that, I might as well just write it myself. But yeah, asking it like, how would I write a function, to calculate the integral of a sine, something like that? Sure, you can ask it, because that's something that it's a very short thing. It's something that it will give you examples of. If you ask it, provide me software to analyze Lisa data, do not trust what it's going to spit out. Okay, and keeping with the data questions and so on, just saw the comment from David. You're traveling back from an entomological expedition. Well, thank you for popping by and clicking the like button. I appreciate that. Okay. And, we're talking about LLMs here, and there was a comment from Scott. Speaking of computation power, I just saw a story a couple of days ago that the cost of the massive power requirements for all of the AI is, in fact, not being paid for by the tech companies, but by all of us, indeed. Yes, that is indeed the case. And, AI, LLM, AI in quotation marks, because there's nothing intelligent about artificial intelligence. It wouldn't pass a Turing test. It's not intelligent. It is artificial. Yes, intelligent. No. Machine learning, these type of things. The cost is huge, and in an era where we know that we have climate change and that we know that everything we're doing is impacting climate change and making it worse, is it really justified to spend that much energy and that much water and that much cooling to get a computer to make art? That's what humans are for. You know, it was supposed to be robots were going to replace the difficult jobs so humans could sit around and make art, not get software to write a poem or summarize a book for you. What's the point? What's the point? That's not, yeah. Anyway, AI rants aside, not a fan. Not a fan of AI, not a fan of LLMs, not a fan of them being used to replace what makes us human. No, if someone sends me an image that is AI generated, I immediately dislike that person. Just as a point. Yeah. Okay, back to the actual questions. There was a question from Lethargo here when I was talking about LISA data. The question was, on LISA, why a data point only every 5 seconds? Are the frequencies low enough that more frequent sampling would be useless, basically? And more frequent sampling would be extremely difficult. So LISA is a combination of 3 satellites that are going to be kept in a triangle chasing after the Earth. These satellites are going to be bouncing lasers back and forth. They're not really bouncing. They send the laser, it gets absorbed and kind of re-emitted, but they have lasers going between the different spacecraft, and then they measure the lasers, then bounce into a test mass, and you can use test masses which are kept in constant free fall to measure any changes in distance. It's very, very cool, very sophisticated. One data point every 5 seconds is kind of ideal, both for what we're looking for and for the technology we have at the time. So that's kind of the sweet spot that we're aiming for. But one data point every 5 seconds over 4 years with an expected uptime of 82%. There will be 18% of downtime caused by either known problems or known software updates, glitches, things like this, but we expect 82% of uptime over 4 years for LISA, which is very cool. There's going to be a lot of data, and a lot of data that we're going to have to analyze, we being, us LISA people. So it's very, very cool. Okay, sticking with this, and then I'm going to go back to some other questions. There were some comment questions I wanted to get to. Another comment from Lethargo when I was complaining about ChatGPT and LLM being used for programming. For whatever it's worth, as a programmer, I definitely agree that humans should make the final code decision. Absolutely. If you get ChatGPT or whatever LLM to help you with your code, please get a human to proof it afterwards. And this also goes for, if for whatever reason you want to cheat on an assignment and ask an LLM to do your homework for you, or your college essay, whatever, proof it afterwards, check it afterwards, because it is very easy for us to figure out when a student has submitted something that has been written by ChatGPT. Because there are basic things to check for that they don't. Even things like ChatGPT uses different punctuation marks to most standard Word documents. And if you just copy and paste something from ChatGPT, the quotation marks are going to be wrong. And that is such an easy thing to look out for. And of course, someone can have a different font, different typographical settings, but by default, if you copy and paste something from ChatGPT, the punctuation is a dead giveaway. So if you're gonna use ChatGPT or any other large language model, at least be smart about it and make it harder, and not for us to just be like, yep, robot wrote this, next. If you're gonna do that, I saw something recently, back in my day, if I wanted to cheat on an assignment or on an exam, I had to put effort into it. And usually the effort you'd put into cheating on an exam or on an essay would already help you learn. If you wanted to write all your formulas or your equations and slip it under your calculator, you're probably going to memorize the formulas while doing that. But if you ask ChatGPT to write an essay, what are you getting out of it other than the grade? Anyway, yes, this is something I will rant about at length. At length. Okay, moving on from ChatGPT. I am not working with LLMs, as you might have gathered from the rants. But I do work on very cool codes written by very cool people. And that is fun. Also, humans make mistakes. Codes are buggy. It happens, but that's part of the fun. Coming from Paul, I love writing with M dashes, and then ChatGPT started doing it, making my writing suspect. Yeah, as a fellow M dash user, I agree. M dashes are great. It's one of the most underrated punctuation symbols. I use it in all of my writing. And then now it's considered like a telltale sign that ChatGPT wrote it because ChatGPT uses a bunch of M dashes. Unfortunately, or fortunately, most researchers that I know also use M dashes. So that is not something that I would consider a sign of ChatGPT. But the quotation marks, that is an obvious one. And semicolons. Now, as someone who is a huge fan of the use of semicolons, I have opinions on punctuation. Semicolons are great. Most people use them wrong. Most people do not know how to use semicolons properly. And it's also, if I've had a student submit an essay multiple times or homework multiple times and they've never used a semicolon in their life, and then suddenly there's an essay with a bunch of correctly placed semicolons, I'm not going to believe it. Anyway, yes, if you're going to use LLMs, check your punctuation as a punctuation nerd. Please do it properly. Okay. And yes, of course, if that's not the only thing. I'm not saying like, okay, you have perfect punctuation, it must be written by ChatGPT. But there are telltale signs, and if you're going to use it, do it smartly. And make sure you delete the line of as a large language model, because people don't even bother deleting that sometimes. Anyway, moving on from me ranting about AI, in answer to the question that started all this was, what am I doing in my job? I am working currently on the Lisa Cosmology Data Center, the Finnish Cosmology Data Center on the Lisa part. It's very cool. I wrote a blog post about it. I'll post a link to the blog post down below. I said that 3 weeks ago and forgot to post it, so I'll post it this time. And let's go back up to the top. We were talking about comets, 3L Atlas. David Dunn, the local astronomer in the chat, has confirmed that 3L Atlas will not actually be visible because it will only have a magnitude of about 11, I think you said, yes, brighter than 11th. So it's not going to get a magnitude brighter than 11, so we probably won't see 3L Atlas. But it is a hyperbolic comet, as Lothargo said, so it's going to come by and go away and we'll never see it again. So, it would be nice to see it, but I don't think we're going to be able to see it, at least with your standard telescope or binoculars. Okay, there was a comment from Prath that I want to get to, but let me just check that I addressed all of the comments about both the data center and the rants about AI. Yes. Follow-up from David Dunn about comets. Newly discovered comet Swan might be visible to the eye, but barely. I have not heard of Comet Swan. I guess it's so newly discovered that it has escaped my radar. But yeah, Comet Swan sounds good. I will check it out. Look up Comet Swan, and then look up for Comet Swan, I guess. Yeah, okay. I see a lot of people sharing my thoughts about ChatGPT in the chat, which is always nice. Okay, so then there was a question from Prath, which I haven't read yet, but I'm sure it's going to be a good question, which you've been sat on for a few weeks, apparently. Can the Chandrasekhar limits be exceeded by rotation speeds of the body? I imagine the centrifugal force from rotation helps a little to overcome gravity. That is an interesting question that I'm going to have to just think about, because I'm not completely sure if I've understood the question. Let me just read that again. The Chandrasekhar limit. In 1 sec. So the question is, can the Chandrasekhar limits be exceeded by rotation speeds of the body? I imagine the centrifugal force from rotation helps a little to overcome gravity. And the Chandrasekhar limit is the maximum mass a white dwarf star can have before it would basically collapse. So yeah, there's this kind of limit for white dwarf stars. So white dwarfs are stars that are very, very dense, not yet dense enough to be a neutron star or a black hole, but very, very dense. And there is a maximum limit on how massive they can be. Beyond this, they would be too massive and they would basically collapse. So, yes. Now back to the question. So Chandrasekhar limits maximum mass of a white dwarf, which is about 1.4 times the mass of the sun. If it's any heavier than that, gravity would cause it to collapse. Now, usually in a star, you have a constant battle between gravity pulling things inwards and the pressure caused by the fusion pushing things outwards. Now, in the case of a white dwarf, you actually have something else causing it to push outwards, which is known as the electron degeneracy pressure. Now, the electron degeneracy pressure is basically two electrons cannot occupy the same space. No matter how much you condense an object, you can never force electrons to occupy the exact same space. Now, this leads to an electron degeneracy pressure, which is basically the electrons fighting against being condensed too much. So, in the case of a white dwarf star, you have the battle between gravity pulling things inwards and the electron degeneracy pressure pushing things outwards. And this means that the maximum mass of a white dwarf is going to be 1.4 solar times 1.44 times the mass of the sun. Anything above that, and you can kind of collapse it into a black hole. The gravity, or does it? Yes, if it's too massive, it collapses into a black hole. Even in a black hole, the electrons, it's not like they coexist, but you can just kind of overcome this pressure and push things together a bit more. So, the question, that was just a bit of backstory as to what the Chandrasekhar limit is. And the question was, can this be exceeded by rotation speed of the body? Now, I don't think so. And the follow-up was the centrifugal force from the rotation helps a little bit to overcome gravity. In general, I would say no, because the limit is given purely by the relationship between the electron degeneracy pressure and the gravitational force. And I don't think you can in any way overcome this by making your white dwarf rotate, I believe. So very, very cool question there. Very, very complicated question. I'm going to go with no, but don't quote me on this. So I would say that even if your white dwarf is spinning, which we assume it probably is because most things in the cosmos are spinning, but even if your white dwarf is spinning, I don't think you would be able to overcome the Chandrasekhar limit of a white dwarf, because the Chandrasekhar limit is not inherently rotated, is not inherently connected to the rotation of the white dwarf. So I'm going to say no. Cool question. I'm going to have to check that out. This is also the type of thing that, you know, I studied a long time ago and is somewhere in the back of my brain. It's a problem with science, with any field of science, that you become hyper specialized. And you know, I study cosmology, which means I know stuff happening inside the universe. You know, I've taken courses on astronomy, on astrophysics, on different aspects of stars and galaxies, but my focus is on cosmology, so on the system as a whole. Which means that when we get into specific questions about like how do these stars behave, or if you ask me by memory, what does the Hertzsprung-Russell diagram look like? I could probably do like it's got a line, its temperature, luminosity, but the details lost on me. So yeah, it's the questions about white dwarfs is something that I probably knew at some point when I was studying it, when I was doing general relativity. But right now, it's like, yeah, the Chandrasekhar limit is a thing that we have that is 1.44 times the mass of the sun. Yep. So very cool. I love that type of question. Incidentally, this is one of the reasons I love doing Cup of Cosmology, because I feel like it is very easy in our field to get hyper specialized and to focus really on your topic. And you lot always ask me questions that are a bit out of my topic or just different to what I'm working on every day. Of course, when we're talking about gravitational waves or dark matter, that's stuff I'm working on a day-to-day basis. But then when you ask me questions about comets or about, you know, gravity in black holes, I'm like, okay, this is not necessarily what I'm working on, so let me think about this. And I love it because thanks to all of your questions, I keep thinking about other topics. And it keeps me fresher on a lot of different things, which helps me avoid over specializing, which is always nice and always useful. It's something that something that my PhD advisor told me once. He didn't have a lot of praise because he's not the type to give praise, but at some point he said that I had a very big breadth of knowledge, or very diverse breadth of knowledge, or something like that, which was a good thing because I wasn't becoming too hyper specialized. And that is thanks to all of the questions you asked me. So I appreciate the questions about white dwarfs and Chandrasekhar limits. So my answer is, I do not believe we can overcome the Chandrasekhar limit of how massive a white dwarf can be by making it rotate, but don't quote me on that. I will check afterwards. I will, it's something that should be pretty easy to check, just doing some equations of where the forces are going to check this. Yeah, I will check that one. That's a cool question, as always. And sticking with this, there's a question from Scott of, do white dwarfs have uniform density, or is the core more dense than the surface? See, I would say the other way round. I would say yes, sorry, correct, yes. The core should be more dense than the surface. This is true for most stars, I believe, that the core of the star is more dense than outside, just because of the way mass is distributed in dense objects. Usually you have a peak closer to the center, but like we do with galaxies, we think, maybe to some degree. But I'm not sure how the density behaves in a white dwarf. I would say it's kind of denser in the center. And Prathia followed up with neutron stars have denser cores than the surface, ordinary stars have denser cores than the surface. There's no reason why white dwarfs should be any different. Indeed, given that white dwarfs are kind of somewhere in between normal stars and neutron stars, and we know that neutron stars have more density at the core than on the surface, and we know that normal stars have more density in the core than on the surface. The same should hold for white dwarfs. So we expect there to be more density at the center and then less as you reach the surface of the star. But yes, very cool questions. But yeah, when you ask me about white dwarfs, it's a bit far from what I work on, but I love the questions. It's the thing about being a cosmologist means I look at the universe as a whole, I look at the system of the universe, but the exact nature of stuff happening inside the universe is always a bit difficult. An example I can give of this is when we think about what do I work on as a cosmologist, one thing that comes to mind, you're just going to see the wrong image for a minute because of the new restream thing, but one thing that comes to mind in terms of what do I work on as a cosmologist is, of course, the cosmic microwave background radiation, CMB for short. This is the oldest light we have in the universe. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. This here shows us how light was behaving then, and based on how light was behaving then, we can figure out what the universe was made of, how old it was, how old it is, when stars turned on. But this thing here, it's a picture of the whole universe. Every point here is a point in the distant cosmos. Then when you ask me about a single star, it's like, what's a star when you can study the whole universe? Now, of course, I just use this as an absolute shameless excuse to put the CMB image, because I realized we were 38 minutes into the stream and I hadn't shown the CMB yet. So shameless sidestep into CMB there. But yes, as a cosmologist, this is the type of stuff we study. The whole universe, the system, how the universe behaves in general. The individual things, the pieces inside are slightly further away. It's kind of a scale thing. This is also often what I say is the difference between an astrophysicist, an astronomer, a cosmologist, is the scale of what we're looking at. An astronomer will look at things close by, usually within our galaxy or local neighborhood. Astrophysics will deal with things like what are galaxies made of, what are white dwarfs, what's happening with these type of things. And then cosmology is the universe as a whole. What is dark matter, what are gravitational waves, these things that act across the whole universe. But of course, you can also use cosmology to study general relativity, and then you get into gravity or quantum gravity even, and then you might be studying things like neutron stars. There's a very cool thing that sometimes you find that the physics and equations you use to describe one thing also apply very neatly to describe something else. And one very cool example of that is, I'm going to piece together two things that look very different. But first I need a drink because I've ignored my water since we started the stream. Okay, following up before I go on my tangent about cool stuff that doesn't seem connected but is. So comment from Scott here when we're talking about the density of white dwarfs, that you're wondering if the surface could be just below the electron degeneracy limit, but the core could be higher. Not really. Now, even if we're talking about a different density, at no point will you be able to overcome the electron degeneracy limit. This is a limit imposed by quantum physics, and it's not something you can overcome. The electron degeneracy limit is what it is. even when you're making the white dwarf more massive and then it will collapse into a black hole, you're not exceeding, sorry, the electron degeneracy limit. You're just adding enough mass that you can collapse to a black hole without exceeding the electron degeneracy limits. So even though even if a white dwarf does have different density at its core and on its surface, at no point in the white dwarf will you overcome the electron degeneracy limits. Okay, sticking with stars, and then I'm going to change gears. Sticking with stars, there's a type of star that is also not dense enough to be a black hole, but almost, and more dense than a white dwarf, and that is called a neutron star. Now, a neutron star is a star that is so dense you can start to fuse neutrons together. You can kind of push things together. You can push protons and electrons together and make neutrons, which is kind of weird and but something you can do. So a neutron star is made entirely or mostly of neutrons. Now, what's happening inside neutron stars is funky. It's weird stuff. It's just, yeah. When you put a bunch of neutrons together, you have weird quantum effects. You have a bunch of stuff happening, but somehow it's still powering the star. Very cool. As you can see, I don't know a lot about neutron stars other than they're very cool. But something I do know about are phase transitions. Now, phase transitions is something we're pretty used to. If you freeze water, the transition from liquid water to solid is a phase transition. If you heat up water and it boils, you get the transition from liquid to gas. This is a phase transition. Now, there could have been phase transitions in the very, very early universe. As the universe was growing and expanding, we had different forces breaking apart. Now, we know that the universe has 4 forces. I'm going to bring this back to neutron stars. Don't worry, just hold on to neutron stars for a minute. The universe as we know it is governed by 4 forces. We have the electromagnetic force, electricity, magnetism. We have gravity, pen falls down, we orbit the sun, gravity. We have the strong nuclear force, which holds things together at the atomic level, holds neutrons and protons together inside nucleus, holds quarks together inside the protons and the neutrons. And then we have the weak nuclear force, which is responsible for radioactive decay and a bunch of other cool things like neutrinos. Okay, one sec. Okay, just needed to clear my throat a bit there. So, 4 forces. Now, in the very early universe, we believe all of these 4 forces were joined together, potentially. And at some point, they gradually broke away. Now, we don't know if gravity was joined with strong and if strong was joined with the others, but we know for sure that at some point, the electromagnetic force and the weak force were joined together in what is known as the electroweak force. At some point in the very early universe, the electroweak force is separated. So then you get the electromagnetic force and the weak force. They go from being 1 force to being 2 forces. Now, when this happens, it could have triggered a phase transition in the early universe. Now, this phase transition is similar to the idea of water turning from solid to liquid or from liquid to gas. Now, it's not exactly that. We're not saying the universe solidified or evaporated, but it's the same general idea that the universe could have changed its overall structure or markup or stuff that was happening inside the universe based on a phase transition. Now, these phase transitions may or may not have happened in the early universe. Depending on if they did happen, they might have produced gravitational waves, which might be detectable by LISA. So this is why I'm interested in them, because if these forces separated in a specific way, it produces a certain type of phase transition that creates gravitational waves, ripples in the fabric of the cosmos, that would still be everywhere today in the background of the universe. And we might measure them in 10 years with LISA, which is amazing and very cool. And then we're talking about something that happened 13.8 billion years ago, and we might be able to measure that with lasers in space one day. Why not? Very cool. But the cool thing is, going back to neutron stars also have phase transitions happening inside. As the pressure is so high that you're fusing protons and electrons together and you're making neutrons, you are triggering a phase transition inside the neutron star. Or you can trigger. And the cool thing is, the same set of equations used to describe neutron stars, phase transitions in neutron stars, are very, very similar to the equations used to describe phase transitions in the early universe. which is kind of cool. So this is why, even though I say like we don't work on stars as cosmologists, there is actually a group in my institute working on neutron stars, more specifically on kind of the phase transitions that happen inside neutron stars. And a lot of what, when I listen to their research, I'm like, this is very similar to what we're doing, just in a different medium, basically. Like we're doing phase transitions in the early universe, we're doing phase transitions in neutron stars. We're talking the same language here, which is very cool because then inside the Helsinki Institute of Physics, there is a subgroup working on neutron stars, but not as you'd expect with neutron stars and kind of like, as a star, but rather neutron stars as phase transition labs, places where you can study the phase transitions. And that is really, really cool. So, point I want to make here is even if even though scientists and cosmologists we work on very different topics, sometimes talking to each other can be really useful because we figure out like, hey, what you're doing is similar to what I'm doing. The language is the same. We can explain, we can talk to each other. And that is very, very cool. And I love listening to the neutron star people in my office because not only do I learn more about neutron stars, but I learn about how similar things happening inside neutron stars are to stuff we are doing. And also, fun fact, there's also similar phase transitions happening potentially in supercooled helium, which is why there's now some people in my group working on experiments to study supercooled helium because of the similarities, the equations of physics. Very cool stuff. If this is in any way interesting to you, if what I just said made you think like, oh, I want to know more about this, I could try to get a neutron star person from the office to join us on Cup of Cosmology. I haven't had a guest in a while. The reason I haven't had guests in a while is because my own schedule has gotten so erratic that it's very hard for me to fit in guests as well right now, which is why I haven't been guest on Cup of Cosmology in a while. But I do have a few lined up. There was someone who was the first person in Helsinki to join me on Cup of Cosmology several years ago now. She might be interested in doing another Cup of Cosmology very soon, still to be confirmed, but that would be cool. And that would be maybe on quantum gravity, if we're lucky, or on string theory, potentially. We'll see. We might also get someone on neutron stars if that's something that you all think is interesting. So let me know if you want to know more about neutron stars and how they relate to physics of the early universe. Let me know, and I'll try to get a colleague to come and tell you everything that I'm not able to tell you about neutron stars. So this is a complete tangent. I just jumped off of the question about white dwarfs and the Chandrasekhar limits because that got me thinking about electron degeneracy pressure. And from there, I went to neutron stars. And from there, I went to the similarities with neutron stars and early universe cosmology. So if you wonder how my brain works sometimes, chaotically. Like you can ask me about white dwarfs and I'm going to be like, let's talk about this slightly vaguely tangentially related thing. Because lets me slip in the CMB and it lets me tell you that research is cool, especially when we talk to each other. Okay, some very good questions here. One from Paul. Do you think we'll someday be able to experiment? Okay, there was another question that I'll go back to in a minute because I just want to stick on this topic. And then there's a question about the CMB that I need to go back to. Question from Paul. Do you think we'll someday be able to experimentally recreate circumstances to unify the forces that broke apart early in the universe? Probably someday, yes. I don't want to say we'll never have the technology to do this, but it is very, very difficult. Like the energy levels involved are huge. When the universe was in its infancy, it had a huge amount of energy. Now we can already get pretty close to it, not to that exact temperature, but at the Large Hadron Collider, where we smash particles together and see what happens, we can get to higher energies. And the idea is to try to reproduce things that happened in the early universe, maybe reaching the point where we had a quark gluon plasma, where quarks and gluons were kind of in a mushy state instead of being separate things. So we do try to push to these levels. And I don't want to say, no, we'll never be there. But right now, it would be very difficult to do an experiment that reproduces the energy we would need to test the theory of everything. So you might have heard of grand unified theory and theory of everything. These are describing basically theories that explain how forces are tied together. Now, we know that the electromagnetic and weak forces were together as the electroweak. This is fine. If you want to add the strong force into it, you get the grand unified theory. If you want to add gravity into this, you get the theory of everything. And the theory of everything is the one that is going to be the hardest to experimentally test and in any way to describe, because we have a pretty good understanding of three forces. Gravity is weird. You might think gravity is the force we're most familiar with, it's the one we understand the most. No, gravity is the weirdest force. It can be described as a force. It can also be described as objects bending space-time and space-time telling objects how to move. It's a geometrical force. So then and it acts on vastly different scales. All of the other forces act on small scales. And then you have gravity, that's big scales. How do you put gravity together with the quantum world? Weird, we don't know. This is what quantum gravity tries to do, is what string theory tries to do. And this is what would lead us to a theory of everything. So theoretically, we're not at the stage to describe a theory of everything yet. And experimentally, it's going to be quite a while until we can get to these energies. But I don't want to say never. 100 years ago, Einstein said we will never measure gravitational waves, and we have. So I don't want to say like we will never measure this, but at least right now it's going to be quite difficult. But yes, it is something that is, I hope, will happen in the future, and it's something that physicists are working towards. Follow up from Prath when I was talking about the electroweak force separation. When you say the electroweak force split, did the field split into two everywhere at the same time, or it split at one point and that propagated through the field to everywhere? Excellent question, Prath. We believe the latter. Now, depending on how the electroweak force is separated, the exact mechanism is not completely clear. Did that trigger inflation? Did inflation trigger the separation of forces? Did the Higgs boson turning on trigger the separation of forces, or was that a consequence of the forces separating? But one way that we think about it is, especially coming at it from the phase transition angle, is if we imagine that the forces being united is one energy level, but the forces being separate is a different, lesser energy level for the universe. Now, what can happen is some point in the universe tunnels to this lower energy stage where it's more energetically favorable. So at some point in the universe, the forces separate. And once one part of the universe is there, that is going to kind of propagate everywhere. Because it's like once the universe realizes there's a lower energy, all the field around it is going to follow it down to that lower energy. Now, one picture that we often think about in terms of if this separation happened as a phase transition is you might get bubbles of the new fields or the new structure, the new phase. So you can imagine bubbles might appear where inside the bubble the forces are separate and outside they're still unified. Now, inside the bubble has a better energy state. So I've just realized, don't pay attention to my hand gestures here. So you have your bubble. Now, inside the bubble, you have a different, more energetically favorable state than outside the bubble. So this bubble is going to gradually grow. Multiple bubbles are going to appear. They're going to gradually grow, take over the universe, and replace the old phase with the new phase, where the old phase might be forces unified and the new phase might be forces separated. This is a very simplified picture. But yes, it's an excellent question. And it's a question from Paul here. Sorry, it's a question from Prath here. So usually the picture we think of is that somewhere in the universe the forces would separate, and this would then propagate to other parts of the universe. Follow up, if the universe moves to a lower energy level, where does the delta go? Excellent question. Yes. We're talking about kind of the field tunnels to a lower value. So there's not really an energy loss here. It's just that you're tunneling to a lower energy state. Yes. I'm not going to give a more advanced answer than that because I'd have to bring up the equations and the math and actually prepare it. That's an excellent question, though. I like the thought pattern there. A follow-up from Scott here, and then there was already a follow-up from Prath about your own question here. If it's a point spread, I don't see how the spread could be faster than light, and since expansion happened faster than light, there could still be parts of space where the split hasn't happened. Yes. This is why, whenever we talk about stuff in the universe, we always limit it to the observable universe, the patch of the universe that we have in any way been able to have some type of contact with. And that's the only thing we can talk about. Now, we're not talking about the part of the universe we have observed. We're talking about the part of the universe that is theoretically observable based on the speed of light and based on the expansion of the universe. There is only a bit of the universe potentially that we can talk about. The observable universe has a finite size, and all of the physics we're talking about is inside our observable universe. Now, the question as to whether there could be other pockets in the universe where the forces are separated in our universe, has that propagated in our observable universe, has that propagated everywhere? Not necessarily. And this leads us very nicely into the idea of the multiverse. Now, we often think about the multiverse, thanks to science fiction, we might think about the multiverse as being multiple parallel realities. But a way that we think about the multiverse in terms of cosmology is potentially this idea that there could be other patches of the universe outside our reach that have slightly different laws of physics, where the universe expanded so quickly in our bubble, and potentially stuff that's happened in our bubble observable universe has not yet spread to other observable universes. And this could lead you to the idea of the multiverse, where we could be in some type of like quantum foam full of, or imagine like a sponge or a foam, and every pocket is its own universe with different laws of physics. This is something that unfortunately we cannot actually prove or disprove because we are limited to the information contained within our own universe. So the question here, excellent question from Prattle, the observation here that if you have the electroweak forces breaking in one part of the universe and this is propagating at the speed of light or slightly less because of friction, but let's say at the speed of light, it could be that there are patches of the universe that never experience this. So, excellent question, Pratt. You're thinking like a multiverse person now, because that is exactly what leads you to that. And then follow up from Scott, very connected to this. Based on this discussion, maybe the vacuum decay wouldn't be so bad. Sure, it would destroy everything we know now, but what comes after could also be cool. Excellent point, Scott. And I'm glad you related what I'm saying to vacuum decay of the universe because it is the same physics. It is exactly the same physics. Now, the vacuum decay of the universe is this idea that what if one of the fields, for example, the Higgs field, suddenly finds a lower energy state? The potential field of the Higgs could tunnel to a lower value of potential energy. There's a question here from Lathargo. Are we talking about energy or energy density? We're talking about potential energy. And the field, the kind of the potential energy of the field. So the field is what tunnels to a lower state or travels to a lower state. So the question here of the vacuum decay, the idea of the vacuum decay is that what if one of the fields that govern our universe today, for example, the Higgs field, which gives everything mass, what if this tunnels to a lower state and drags the whole universe with it into a new phase transition, a new state of the universe? If this were to happen, the universe as we know would be deleted. Think of Thanos snapping fingers, but across the whole universe, and not just life, but planets. The laws of physics might snap out of existence. And our universe could be replaced by an entirely new universe with potentially different laws of physics, different state, different phase. Now, we don't think this is likely to happen based on everything we know about fields around us. We don't think any of the fields are set to trigger vacuum decay. But if it does, if the vacuum decay happens at any point in our observable universe, it will spread and it will reach every point of our observable universe and it will drag us down with it. It's a question of if you wait enough years, however unlikely it is, are we actually going to have a vacuum decay at some point? Now, Scott's comment of maybe vacuum decay wouldn't be so bad because we are going to replace our universe with another universe if vacuum decay happens. Sure, maybe it's not so bad. We do get a new universe, but we wouldn't be able to live in it. We would be gone. Our universe would be gone. If you want to think about that as just being the natural evolution of the universe, that's cool. That's how I think about it. If vacuum decay happens, it's just a natural occurrence of events in the universe. But it might not happen. I'm not afraid of the vacuum decay happening anytime soon. But if it does happen, we would never see it coming. It's the great reset button, deletes the whole universe without any warning. You would never see it coming. It would just suddenly hit you. Because it would travel at the speed of light, by the time we saw it, it would already be upon us. Yeah, so coming from fact, you weren't thinking along the lines of the multiverse, just separate states of fields in our own universe, observable and unobservable together. This is exactly leading into the multiverse, though, because again, everything we can talk about is inside our observable universe, and we know that inside our observable universe, the weak force has separated from the electromagnetic force. Outside of our observable universe, we have no idea. Could there be a different part outside of our observable universe where the laws of physics are different? Yes. Where electroweak hasn't separated? Hypothetically, yes. And that you would describe as a slightly different universe to ours, the multiverse. So yes, there could be patches outside of our observable universe where the electroweak forces have not separated, but it's something that we will not be able to measure from our universe, because we are limited to the information contained inside our observable universe. So even if you weren't thinking along the lines of the multiverse, your question was very much leading into the multiverse, because when you're talking about different pocket universes or separate universes with different laws of physics, different observable universes with different laws of physics, that is what we kind of call the multiverse in the context of cosmology and inflation. And cool questions. I love these questions. We've gone in a very interesting direction here. And sticking with this, I know there's still a CMB question that I need to get to about what comes after Planck. I will get to that one later. That was a question from Lethargo, but sticking with this. This was a great question. That was a great series of questions here. So we covered the electroweak force separating. Comment from Lethargo that more info about neutron stars sounds cool. Absolutely. We can. I will see what I can do. I'll see if I can get a neutron star person to come talk about stuff. Okay, so we were talking about weak force. There's a question from Anshia, which is a very fun question, and I'm not sure if it's an intentionally like poking question, but it is a very fun question that is easy to get a reaction out of physicists from. The question is, what do we know about the weak force? Excellent question. And yes, it's an excellent question that is always a bit so I said there's four forces, right? Like gravity, pen drops, we're in orbit around the earth, black holes. We pretty much think we understand gravity, we think. There's the electromagnetic force, electricity, magnetism, good stuff. There's a strong force, it holds stuff together. It's strong, it glues things together. And then the weak force, and I do something like radioactive decay, moving on. And then I say there's one force that we don't understand. So you'd think the one we don't understand is weak force, because I just mumble radioactive decay and move on. But the weak force is the most well understood force. The one we don't understand is gravity. But the problem is the weak force is very difficult to intuitively get an idea of. Now, the strong force makes sense. It glues things together. It's strong. It holds things together. Makes sense. When we think about gravity, it's something that intuitively we can kind of understand, even if not the technicalities of quantum physics and stuff. We can get an idea of how gravity behaves at the quantum level. We can get an idea of gravity. We can get an idea of electromagnetism. Weak force is the one that is the most unintuitive and difficult to explain. So there's often the joke that asking a physicist about weak force is kind of like, oh god. But I appreciate the question. So the weak nuclear force is responsible for radioactive decay. So it has three particles that carry the force. We know that forces are carried by particles. The strong nuclear force is carried by gluons, they glue things together. The electromagnetic force is carried by photons, particles of light. The weak force is carried by W and Z bosons, and there's two W bosons and one Z boson. And the thing about the weak force is it's the one that is responsible for bigger atoms or bigger elements decaying into smaller ones. So for an example, everything that's happening in a fission reactor where you're splitting things apart, you're splitting atoms apart, that is related to the weak force, but also the strong force, because really the energy you're getting from fission is from pulling apart the strong force. So the weak force is kind of radioactive decay. If you have any radiation, think Chernobyl or anything like that, you might have heard of things like alpha particles, which are the damaging radiation, or beta radiation, gamma radiation, if you like the Hulk. Alpha and beta radiation, at least, are caused by the weak force. So it's kind of a way of decaying some some elements, but not all of them. And it's also the only way that dark matter might interact with the rest of the universe, except for gravity. So we know that that dark matter is this invisible matter that is occupying a lot of the universe, 25% of the energy budget of the observable universe. Dark matter interacts via gravity, it doesn't interact via the electromagnetic force. However, we usually say that's like everything we know about dark matter, but one of our biggest ideas for dark matter is what is known as a weakly interacting massive particle. So a particle that it interacts weakly, it has mass. It's weakly interacting massive particles in the name. And this is saying that in the early universe, apart from gravitational interactions, dark matter could be weakly interacting, so interacting via the weak force, which means it would basically talk to the W and the Z bosons, which would then talk to normal matter. And if this is the case, then dark matter would have somehow been related or connected to matter via the weak force. So one of the ways we try to search for dark matter is by triggering this weak interaction, and this is searching for WIMPs. So the question really was just what do we know about the weak force? So that was a few things that we know about the weak force, but the weak force is always the one that is hardest to explain potentially because it's the least intuitive one. It's like alpha particles, beta particles, radioactive decay, Chernobyl. You can throw about these ideas, but the strong force is intuitive. It glues things together. Done. Gravity is intuitive to some degree. Electromagnetism is intuitive. Weak one I find is not intuitive to either understand or to explain. But the thing that we know the most of is that it causes radioactive decay. It's also the way that neutrinos interact with other particles. So usually if you have a weak interaction happening, you're going to produce neutrinos. Neutrinos are these tiny particles that travel almost at the speed of light, but not quite. They have a tiny, tiny mass, and they're zipping through us. Like every second, 60 million neutrinos passing through the tip of my thumb. But they don't affect us because they only interact very weakly via the weak force. So yes, what do we know about the weak force? It is difficult to explain, but it is a very cool force. I hope that answers the question, but yes, it is a very difficult question, but a very cool question. If anyone here is familiar with XKCD, you might have noticed that I was referencing a particular comic. So XKCD is a webcomic that is done by a former physicist, and it covers topics of physics, math, love, sarcasm. I think that's actually the tagline. And it's very funny, and it's been going for so many years that it's become a joke in like nerdy spheres that whatever situation you're in, there is an XKCD about this. And there is an XKCD about the forces, and it's literally this where someone's like, okay, I think, what are the four forces? And the scientist answers and says, and we don't understand one of them. And the person's like, the weak force? Because you didn't explain that one properly. It's like, no, we don't understand gravity. Weak force is good. We just don't know how to explain it. So yes, great question. Slightly complicated question. Unintentionally difficult question, I believe, but it's a very cool question. Okay, sticking with this, still need to get back to the CMB question. Sticking with this idea here, there's a comment from Paul. I've heard that what makes gravity unique is it interacts with all matter the same way, as opposed to electromagnetic, which doesn't. And this is the reason we can't interpret it as geometry. Yes, we can interpret it as geometry, exactly. So gravity interacts with anything that has mass. If you have mass, you interact with gravity, but mass is kind of an intrinsic, well, not really an intrinsic, but it's a property of the matter itself. Whereas the other forces, as I mentioned just now, forces are carried by a particle. The gluons, which glue things together, carry the strong force. The W and the Z bosons carry the weak force. Photons carry the electromagnetic force. What carries gravity? What causes gravity? Mass. What carries gravity? We have no idea. And this is kind of why it's very hard for us to put gravity together with the other ones, because it interacts with everything that has mass in the same way. Whereas, the weak force will depend on if something interacts with W and Z bosons. The electromagnetic force depends if something interacts with photons. Dark matter doesn't interact with photons. This is why it's invisible. Strong force. If you have enough gluons, you're going to have a strong force. But gravity is like mass. How do we deal with that? Yes, so it is a very good way of explaining it, that what makes gravity unique is it interacts with all matter in the same way. Dark matter too has mass, interacts with gravity. Another question here from Prath. Is there a quark degeneracy pressure that provides another barrier to black hole formation beyond neutron degeneracy? What about gluon degeneracy pressure? Knew this one was coming. So the thing about gluons is gluons kind of exist as a soup, which does not really help in any way with the way I'm going to answer. So we can usually go like, hey, here's a photon, here's a Z boson, here's a W boson. Gluons are kind of a swarm. So inside a proton, you'll have three quarks, you have two ups, one down, and you have a sea of gluons which kind of bind everything together. Gluons have such a strong presence that then if you try to pull two quarks apart, you're actually just going to create enough energy that you create two new quarks. You can't have quarks alone because quarks are surrounded by this kind of gluon soup which binds them to something else. So gluons don't exist individually. Now, the question was not about gluon. Yes, the question about gluon degeneracy pressure is much harder because gluons are just kind of a soup. You have a soup of gluons, which is not a helpful answer, but a fun fact. Gluons are a soup. This is what we talk when we're talking about the quark gluon plasma. It's a stage where you had so many quarks and gluons that it was just kind of like the quark gluon soup, which we call a plasma because it's a more technical word than soup. So, is there a quark degeneracy pressure? Yes. Is there a gluon degeneracy pressure? No. So, quark degeneracy pressure is also this idea that you cannot condense quarks to exist in the same place either. But it is, I was going to say it is not as strong as the Fermi degeneracy. Now I'm debating quark degeneracy pressure. And I feel like this is not the first time you've asked this question, Prath, like rephrased, because somewhere on my list of questions from a different week is quark confinement, which is related to quark degeneracy and still a question that I don't have a proper answer to. So I'm going to say, yes, there is a quark degeneracy pressure. It's very different to the electron degeneracy pressure, but I'm not going to answer beyond that because that is a very complicated question to answer. Love the question, Prath. I need to think about it more. I've got quark degeneracy circled on my notes from a few months ago, I believe. Let's save the quark degeneracy and gluon degeneracy questions for when I get a neutron star expert. If I get a neutron star person to come on the stream, you can ask them everything you want about quark degeneracy. I'm going to throw it at them. I have no idea who I'm going to pick on to do this, but when I get my neutron star expert on the stream, you can ask him all your questions about quark degeneracy because that is relevant for neutron stars. Excellent question. Okay, I'm going to go back. This has been a really fun tangent. I brought up neutron stars just to connect it to white dwarfs and cosmology, and then we went down the path of quarks and degeneracies and the vacuum decay of the universe and phase transitions. Absolutely brilliant questions. And there was one question from Lothargo that contained the word CMB, and I need to answer that one. Where is it? Yes. Question from Lothargo asked about half an hour ago by now. Is there a successor to the Planck mission planned for an even better view of the CMB? If so, what additional things would it be hoping to learn? Excellent question. Excellent question. So just a reminder, Planck is the satellite that gave us this image here, if it loads. The cosmic microwave background radiation as imaged by Planck. Now, Planck was not the first one to image the CMB. There have been ones before. There have been predecessors. For an example, WMAP, which gave us this image here. This is the WMAP, the Wilkinson Microwave Anisotropy Probe. This is one that gave us this map back in 2009. It's so cool. We put it on a beach ball. This is my CMB beach ball. Perfectly legally acquired CMB beach ball. So we had WMAP, then first we had COBE, then we had WMAP, then we had Planck. Now, there are also a bunch of missions on the ground trying to do the same thing, measuring the CMB, the cosmic microwave background radiation. There's different advantages to like space-based versus ground-based ones. Now, with a space-based mission like Planck, you can look all the way around the sky. You can get this full CMB, full sky map of the CMB. With a ground-based mission, you can stare very deeply into one patch of the sky, which means you can get more accuracy. Now, if you want a bigger map, of the whole sky to get more overall information. You want a space-based one. For a ground-based one, you're going to get information on a small part that you're staring at very specifically. And this is very complementary because with the all sky map, you get information on how things behave on large scales, whereas when you go ground based, you can push it to smaller patches of the universe, to really small, precise patches. And ideally, you want both of these working together so that you can get information of everything. So currently, there are several really cool ground-based missions taking information, taking pictures of the CMB, which is pushing it to smaller and smaller scales. So things that happen at smaller scales in the universe, like smaller sizes, tinier patches of the universe. We have the Atacama Cosmology Telescope, which I believe has now finished taking data. We have the South Pole Telescope, which is also focusing on polarization, so which way the photons in the CMB vibrate. And based on that, you can also get more information. Now, upcoming mission, we have the Simons Observatory. The Simons Observatory is going to be a ground-based mission that is hoping to push this even further, push it to even smaller scales by getting better telescopes and staring very deeply at one patch of the sky. Simons Observatory, I believe, should be taking data any day now. It's either completed or very close to completion. Now, in terms of space missions, we already have this amazingly detailed map of the sky from Planck. But there is still more to be done, especially in terms of polarization. So again, this is the direction that the photons propagate or vibrate in. We know the photons are coming towards us, but they might be vibrating up, left or right, circular. And based on this, we can get more information about what the photons were doing when they were produced. So there are space-based missions planned hoping to really measure the polarization of the CMB. One of them is LightBird. LightBird is going to be focusing on what is the so-called B-mode polarization, which is a specific way that photons can vibrate, which could also be influenced by gravitational waves. So a B-mode mission might, for an example, be able to measure gravitational waves produced by inflation, which leave an imprint in the way the CMB photons vibrate. So successors to Planck, I think there are ground-based ones. Atacama Cosmology Telescope, the South Pole Telescope have provided a huge amount of information since Planck. Simons Observatory coming up is going to take this further. And then we have things like LightBird in the future, which is a Japanese space agency mission, which is going to measure more in terms of polarization. And then what other ones can we think of? LightBird, CMB stage 4. What else is missing? I'm missing a space-based one that is just gone from my brain right now, but these are the main ones that we can think of. Simons, LightBird, these are next generation CMB missions. So yeah, there is still stuff to do after Planck, after the CMB that we have. In fact, the first conference I attended as a master's student, or no, it was like just finishing my master's, about to start my PhD. So this was 2016. That seems like a long time ago. 2016. I went to a conference that just had the title of Cosmology After Planck, What's Next? And it was all about everything else we're going to do with the CMB. CMB is not over with Planck. There is still so much more to get out of the CMB. That is also when I was first introduced to the topic of spectral distortions and fell in love with the topic. Been a side project of mine for years. I have a couple papers on it. And spectral distortions are basically another thing hidden in the CMB that has not yet been exploited because it's extremely hard to measure. And it's basically related to how the CMB is emitting light. So the CMB is what we call an almost perfect black body, which means it emits light at all frequencies at the same time. So even though we have our photons with specific temperature, they cover all possible frequencies. If the CMB is a black body, that is. Now, we know that the CMB is an almost perfect black body, but there are tiny, tiny, tiny deviations from being a perfect black body. And these tiny deviations produce spectral distortions from the perfect black body spectrum. And if we ever measure spectral distortions, we'd unpack a huge amount of information that we don't yet have access to. And I learned about this at the Cosmology After Planck conference, fell in love with them, and then during my PhD, put out 3 papers on the topic of spectral distortions. Well, 2 during my PhD, 1 after, something like that. But yeah, and maybe someday I'll come back to spectral distortions. I know I can do. I have done a whole stream about spectral distortions, but I can do it again. So, what is next after Planck? We have some ground-based missions ongoing. We have some future ones planned. We have Lightbird, and maybe someday we might get a spectral distortion mission if we're lucky. Okay, final comment here from Prath. Quark confinement was about if virtual particle generation can make a quark-anti-quark pair, and could you get a solar quark if this happens at the edge of a black hole? Yes. Ask my neutron star expert. I'm just going to offload all of the quark confinement questions and quark degeneracy questions to a neutron star expert. I need to figure out who I'm picking on. I have one potential victim in mind. Guest, not victim. I have one potential guest in mind. And yeah, let's see if I can get him on the stream. Okay, no, I have 2 potential people in mind. We'll figure it out. Okay. An hour and 20 minutes in. I think I've answered all of the questions. I believe I have answered all of the questions. It's been super cool questions today. We obviously talked about comets at the beginning. We talked about my cosmology data center and what I'm doing with the cosmology data center. I went on a rant about AI. We then jumped into things like white dwarfs. And from white dwarfs, we went into neutron stars. And from neutron stars, we went into phase transitions, and then the expansion of the universe, the multiverse, pocket universes. We've covered a lot of topics today. And of course, the weak force, the strong force, all of this, gluon soup for dinner. We've covered a lot of topics today. This has been great fun. Thank you for all of these very, very cool questions. Anytime I start a cup of cosmology, unless I have a topic prepared, I'm like, I wonder what we're going to talk about today. And I generally rarely see it coming, because you always take the streams in such fun directions. Like if you'd asked me 2 hours ago what we might be talking about today, I genuinely thought I thought someone was going to ask me about have we found a black hole in the center of a star, because it's been in popular science articles this week. No, we haven't. Spoiler, no. I thought that was the type of questions we would be talking about today, but no, we went down completely different tangents and directions, and I love it. I love all of the cool questions, and some of the questions have been super advanced today, like quark confinement, quark degeneracy. We went into the multiverse and back. This was an excellent series of questions, so thank you, everyone. I love all the questions you come with, all of the energy. I love the energy you all bring to the stream. So let me just check my calendar to see if Cosmology is happening next weekend. It's honestly so hard to keep up with my calendar these days. I have had plans the last 7 weekends. I did manage to fit in a stream for the anniversary special and another one, but I have had plans the last 7, 8 weekends even. Next weekend I have plans. Then I have a weekend off. Then I have 5 weekends back to back of plans. Okay, so conclusion is I'm not 100% sure if there is a stream next week. It will depend on how tired I am from my Saturday plans, and I'm not yet sure what my Saturday plans are, other than I have plans. I do too many things. That is the takeaway here. But Cup of Cosmology might be back next Sunday, still to be confirmed. In any case, at some point, I'm going to try to do a stream about neutron stars. I will give you plenty of warning as to when that's happening so that you can mark it off in your calendars. If you want to make sure you get notified before the next live stream, make sure you subscribe to the channel and turn on notifications, and then you will be notified 30 minutes before I go live, assuming I set the stream up in advance, which I normally do. So make sure you subscribe to be kept up to date about all upcoming live streams. Cup of Cosmology might be back next Sunday, still to be confirmed, but in any case, if it's back, it would be at 8 p.m. Finnish time, at 7 p.m. European time, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com so that you can figure out when the next stream is in your own time zone. Thank you for joining everyone today. There's been so many cool questions, cool conversations. It's been great to have you all here. I'm going to go rest, almost an hour and a half. Good time to finish the stream. So thank you everyone for being here. I hope to see you back again, maybe next week, if not in 2 weeks. I hope in the meantime, you all take care of each other. and stay curious.